March 15, 1944. A coastal defense battery near Anzio, Italy. The night air hung thick with smoke from burning ships offshore, as Oberstleutnant Friedrich Weber pressed his binoculars against tired eyes, scanning the darkness for the Allied bombers his spotters had reported approaching from the south. His flak crews stood ready at their 88mm guns, waiting for the searchlights to illuminate targets they could engage. But tonight, the searchlights revealed nothing. The bombers remained invisible, concealed somewhere in the moonless sky above, yet his radar operators were reporting something impossible. Their Wurzburg radar sets, the most sophisticated fire control systems Germany possessed, were being overwhelmed by something they had never encountered. The screens showed not aircraft positions, but chaos. Dozens of false returns, phantom targets that appeared and vanished, electronic noise that made accurate tracking impossible. What Weber could not yet comprehend was that 8 miles above the Mediterranean, an American B-24 was painting his entire defensive position with invisible electromagnetic energy, mapping every gun, every radar installation, every vehicle with a precision that would have seemed like science fiction just months earlier. The aircraft carried an SCR-584 radar system, a device so revolutionary that it would render every assumption about air defense obsolete within weeks of its combat debut. The psychological impact would prove even more devastating than the tactical advantage. German and Japanese commanders, who had built entire defensive strategies around the limitations of early radar technology, were about to discover they had been fighting blind, while the Allies possessed clear vision in complete darkness. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of how one radar system fundamentally altered. The balance of air warfare begins not on Mediterranean battlefields, but in the laboratories and testing grounds of the United States, where a team of engineers and physicists worked against impossible deadlines to solve a problem that threatened Allied air operations across every theater of war. In early 1942, the United States Army faced a crisis that few outside classified circles understood. Anti-aircraft artillery, despite consuming enormous quantities of ammunition and deploying thousands of guns, was achieving hit rates so abysmal they bordered on statistical irrelevance. German aircraft attacking American positions in North Africa were being engaged by massed anti-aircraft fire that filled the sky with exploding shells, yet the vast majority of aircraft escaped unscathed. The mathematics were brutal. American 90mm anti-aircraft guns, the backbone of heavy air defense, required an average of 1,600 rounds to achieve a single aircraft kill under combat conditions in 1942. Some engagements consumed thousands of rounds without scoring any hits whatsoever. The problem was not the guns themselves, which were mechanically sound and ballistically capable. The problem was fire control. Hitting a target moving at 250 to 300 miles per hour, at altitudes ranging from 5,000 to 25,000 feet, while the target maneuvered unpredictably, required predicting the aircraft's future position with extraordinary precision. The shell took 15 to 20 seconds to reach altitude after firing. During that time, an aircraft traveling at 250 miles per hour covered over 1 mile. The gun crew had to aim not at where the aircraft was, but at where it would be when the shell arrived at that altitude. This calculation involved multiple variables: current aircraft position, current aircraft velocity in 3 dimensions, aircraft heading, rate of turn if maneuvering, wind speed and direction at multiple altitudes affecting shell trajectory, air density affecting both shell trajectory and aircraft performance, and the time of flight for the shell to reach the target altitude. Human operators using mechanical fire control computers could not process these variables quickly enough or accurately enough to achieve acceptable hit rates. The Army's standard M9 Director, introduced in 1941, represented the state-of-the-art in mechanical fire control. This complex analog computer weighed over 2 tons and required a crew of 8 highly trained specialists to operate. The system used optical rangefinders to determine target distance, mechanical computers to calculate lead angles and elevation, and electrical systems to transmit firing solutions to the guns. Under ideal conditions, with a non-maneuvering target at constant altitude and speed, the M9 could achieve reasonable accuracy. Under combat conditions, with targets taking evasive action, often partially obscured by clouds or haze, with visibility limited by smoke or darkness, the system's effectiveness collapsed. The optical rangefinders that the M9 depended upon could not function in darkness, fog, clouds, or smoke. This meant that night bombing raids faced almost no effective anti-aircraft opposition. German and Japanese aircraft quickly learned that attacking under cover of darkness or poor weather provided near-complete immunity from ground fire. American commanders watched helplessly as enemy bombers destroyed ships, supply depots, and troop concentrations during night raids that defensive guns could barely oppose. The strategic implications were profound. If Allied forces could not protect their positions from air attack during half of each 24-hour period, offensive operations would face constant disruption. The solution required technology that did not yet exist in operational form. What was needed was a radar system that could track aircraft with sufficient precision to provide fire control data directly to anti-aircraft guns, eliminating reliance on optical systems. The radar would need to determine not just the general location of an aircraft, but its precise position in 3 dimensions, with accuracy measured in yards, not miles. It would need to track multiple targets simultaneously as bomber formations approached. It would need to operate reliably in any weather, day or night, through smoke and clouds, and critically, it would need to process this information fast enough to generate useful fire control solutions for targets maneuvering at combat speeds. In early 1942, no such system existed anywhere in the world. British radar development, while advanced in many areas, had focused primarily on early warning and general aircraft detection rather than precision fire control. German Wurzburg radars provided some fire control capability, but with significant limitations in accuracy and tracking speed. Japanese radar development lagged significantly behind both Western powers. The United States Army Signal Corps, responsible for radar development, established a research program at the Bell Telephone Laboratories in New Jersey, drawing on the company's expertise in electronics, communications, and systems integration. The project received the designation SCR-584, following the Army's nomenclature system where SCR indicated Signal Corps Radio. The technical challenges were formidable and unprecedented. The radar would need to operate in the microwave frequency range, using wavelengths of approximately 10 centimeters to achieve the narrow beam width necessary for precise tracking. This required developing a practical cavity magnetron, the revolutionary microwave generator that British scientists had invented and shared with American researchers in 1940. The system would need sophisticated antenna design that could scan rapidly, while maintaining beam coherence. The electronic circuits would require unprecedented precision and reliability, operating at frequencies where component behavior was not fully understood. The mechanical systems that physically pointed the antenna would need accuracy measured in fractions of degrees while tracking targets moving at hundreds of miles per hour. And the analog computers that processed the radar returns would need to calculate firing solutions in real time, updating continuously as targets maneuvered. The development team, led by Dr. Hendrik Bode of Bell Labs, assembled engineers and physicists from multiple disciplines. They worked 7 days a week through late 1942 and early 1943, testing prototype components, refining designs, solving problems that had never been encountered before. The cavity magnetron, operating at 3.2 GHz frequency, generated peak power output of approximately 285 kilowatts. This enormous power, focused through a parabolic dish antenna approximately 6 feet in diameter, created a radar beam so narrow and intense it could track individual aircraft with unprecedented precision. The beam width measured approximately 1 degree, compared to 10 or 20 degrees for earlier warning radars. This narrow beam meant that when the radar detected a target, the antenna's precise pointing angle directly indicated the target's position with far greater accuracy than previous systems. The antenna mounting system used a complex mechanical assembly that could rotate in both azimuth and elevation, following targets smoothly as they maneuvered. Servo motors, driven by electrical signals from the tracking circuits, automatically kept the antenna pointed at the target once the operators had designated it for tracking. The tracking was semi-automatic. Operators would detect an approaching target on the radar display, manually position the beam onto that target, then engage automatic tracking. The radar's receiver circuits would then continuously measure the difference between the antenna pointing direction and the actual target location, generating error signals that drove the servo motors to correct the antenna position. This automatic tracking, called conical scan tracking, represented a revolutionary advance. The radar beam was actually tilted slightly off the antenna's mechanical axis and rotated rapidly, creating a cone-shaped scanning pattern. When the target was precisely centered in this cone, the return signal strength remained constant. When the target moved off-center, the signal strength varied in a pattern that indicated which direction the antenna needed to move to recenter the target. This signal processing happened entirely in analog electronics, using vacuum tubes, electrical circuits, and mechanical components, achieving tracking accuracy that seems remarkable even by modern standards. The prototype system first demonstrated successful automatic tracking in October 1942 at the Army's testing grounds in New Jersey. Engineers tracked a B-18 bomber flying at various altitudes and speeds, with the radar maintaining lock even as the aircraft maneuvered. The accuracy measurements stunned observers. The system could determine target range with an accuracy of plus or minus 25 yards at ranges exceeding 15 miles. It could measure bearing and elevation angles with accuracy better than 0.1 degrees. For a target at 10,000 feet altitude and 5 miles distance, this meant position accuracy measured in tens of yards in all 3 dimensions. Such precision had never been achieved with any previous radar system, but accurate tracking alone did not solve the fire control problem. The radar data needed to be translated into gun-pointing commands that accounted for projectile ballistics, wind effects, and target motion. This required integrating the radar with sophisticated analog computers that could perform the necessary calculations in real time. The M9 gun director's mechanical computers were adapted and enhanced to accept electrical input signals directly from the SCR-584 radar. The combined system could track an aircraft, calculate its velocity vector in 3 dimensions, predict its future position, accounting for the shell's time of flight, compute the required gun elevation and azimuth angles, and transmit these continuously updated commands to the anti-aircraft batteries. The entire process, from radar detection to gun laying, happened automatically and continuously with human operators, primarily monitoring the system and designating targets. Production approval came in January 1943, with the first operational units scheduled for delivery by late spring. The Western Electric Company, Bell Labs Manufacturing Division, established production lines in New Jersey and Illinois. Each SCR-584 unit required approximately 3,000 vacuum tubes, miles of wiring, dozens of precision mechanical assemblies, and the massive parabolic antenna. Manufacturing each complete system consumed approximately 3 months of labor from specialized technicians. The unit cost exceeded $100,000 per system in 1943, equivalent to well over $2 million in modern currency. This made the SCR-584 one of the most expensive pieces of equipment the Army deployed, comparable in cost to medium tanks or light aircraft. But commanders who understood its capabilities considered the investment justified. A single SCR-584, directing a battery of anti-aircraft guns, could engage targets with effectiveness that previously required 10 times as many guns firing under optical director control. The first production units reached Allied forces in North Africa in June 1943, just as planning began for the invasion of Sicily. American anti-aircraft battalions received intensive training on the new equipment. Crews needed to master not just the radar operation, but the integrated fire control procedures that linked radar tracking to gun laying. The system was complex, temperamental, and required constant maintenance. Vacuum tubes failed regularly, Mechanical bearings required precise alignment. The magnetron itself, operating at enormous power levels, had limited operational life before requiring replacement. Yet, when properly maintained and operated by trained crews, the SCR-584 transformed anti-aircraft effectiveness so dramatically that German and Japanese pilots would soon report that Allied air defences had become impenetrable. The Allied invasion of Sicily in July 1943 provided the SCR-584's first large-scale combat test. American and British forces brought ashore multiple SCR-584 units to protect the invasion beaches from German and Italian air attack. Luftwaffe commanders, aware that major invasion forces were vulnerable to air attack, committed substantial bomber formations against the Allied beachheads during the critical first days of the operation. The German pilots approached their targets, expecting to face the same anti-aircraft defences they had encountered previously in North Africa. Massed gunfire that filled the sky with explosions but rarely achieved hits. Instead, they encountered something completely unexpected: anti-aircraft fire of unprecedented accuracy that tracked their aircraft through evasive maneuvers and placed bursts exactly at their altitude and position. Pilots who survived their first encounter reported experiences that seemed impossible according to everything they understood about Allied defensive capabilities. The anti-aircraft fire followed them through turns. Shells exploded precisely at their altitude even when they changed height rapidly. The defensive fire was effective in complete darkness, through clouds, in conditions where optical fire control should have been blind. Lieutenant Hans Joachim, a Luftwaffe bomber pilot flying Junkers 88s against the Sicily beaches, survived 3 missions before his aircraft was so badly damaged he was forced to return to base. His debriefing report, later captured by Allied intelligence, described the new defensive environment with barely concealed fear. The Americans have developed some new method of directing their anti-aircraft fire, Joachim reported to his squadron intelligence officer on July 13, 1943. The shells follow our aircraft regardless of evasion. We flew at 6,000 meters, then descended rapidly to 3,000 meters while turning. The anti-aircraft fire adjusted to our new altitude within seconds. Bursts appeared directly ahead of us, forcing further evasion. This continued for 8 minutes until we escaped the defended zone. Our aircraft suffered 17 shrapnel hits. 2 crew members were wounded. This cannot be luck or skilled visual observation. They must possess some detection method that works in darkness and provides exact position information. The German assessment was entirely correct, but Luftwaffe intelligence struggled to determine what technology the Allies had deployed. German forces had encountered Allied radar systems before. The early warning radars that detected approaching bomber formations were well known, but those systems provided only general location information, insufficient for precise fire control. What the Germans did not yet understand was that the Allies had leaped ahead in radar technology, developing microwave systems operating at frequencies German equipment could barely detect, with tracking precision that enabled direct fire control integration. The impact on German air operations was immediate and severe. Luftwaffe commanders were forced to revise their tactical doctrines almost overnight. Formations approaching Allied-controlled areas, now dispersed at maximum distance, accepting reduced bombing effectiveness to minimize exposure to the devastating anti-aircraft fire. Aircraft approaching defended targets were ordered to maintain maximum altitude, trading accuracy for survivability. Losses climbed sharply despite these adaptations. During the first 2 weeks of the Sicily campaign, German air forces lost over 100 aircraft to Allied defences, with anti-aircraft fire accounting for a significantly higher percentage of kills than in previous operations. The statistics told the story more clearly than pilot reports. In North African campaigns during 1942 and early 1943, anti-aircraft artillery had achieved approximately 0.2% hit rates. This meant that 500 shells were required, on average, to bring down one aircraft. By late July 1943, in Sicily, batteries equipped with SCR-584 direction were achieving hit rates exceeding 2%. Some engagements recorded hit rates above 5%, The improvement represented a 10 to 25-fold increase in effectiveness. Suddenly, the same number of guns, firing the same ammunition, were bringing down 10 to 25 times as many enemy aircraft, simply because the targeting had become precise enough to place shells near targets with consistent accuracy. The Italian campaign that followed Sicily's conquest saw SCR-584 deployment expanded significantly. As Allied forces fought northward through the Italian peninsula during late 1943 and 1944, anti-aircraft battalions equipped with the new radar provided critical protection for ports, supply depots, and troop concentrations. The mountainous Italian terrain, which limited mobility and created strategic choke points, made air defense particularly critical. German aircraft attempting to interdict Allied supply lines found themselves facing radar-directed fire that made such missions prohibitively costly. The psychological impact on Luftwaffe crews became increasingly apparent in intelligence assessments based on interrogations of captured pilots. These men, who had been among Germany's most skilled and aggressive aviators early in the war, now described approaching Allied positions with genuine dread. They understood intellectually that their aircraft were still capable, their training was solid, their tactics were sound. But they also knew from bitter experience that Allied anti-aircraft defenses could track them in any weather, at any altitude, and generate accurate fire that gave them little chance of survival if they remained in the defended zone for more than a few minutes. This psychological burden affected mission effectiveness even beyond the actual aircraft losses. Pilots rushing through their bombing runs to minimize exposure to anti-aircraft fire achieved lower accuracy. Formations that dispersed early to avoid concentrated defensive fire reduced their mutual support and became more vulnerable to Allied fighters. The mere presence of SCR-584 radar systems forced changes in German tactics that reduced operational effectiveness across multiple dimensions. The Pacific Theater presented different challenges and revealed additional capabilities of the SCR-584 that would prove even more strategically significant than its anti-aircraft. Applications. Japanese air tactics, particularly the increasing reliance on kamikaze attacks beginning in late 1944, created defensive requirements that pushed radar-directed fire control to its absolute limits. Unlike conventional bombing attacks where aircraft attempted to drop ordnance and escape, kamikaze pilots deliberately flew their aircraft directly into Allied ships. This meant that defensive fire needed to achieve kills with absolute certainty. Merely damaging a kamikaze aircraft was insufficient if it retained enough control to complete its suicide dive. The SCR-584's precision tracking became critical for directing the concentrated fire necessary to destroy attacking aircraft before they reached their targets. The Battle of Okinawa, fought from April through June 1945, represented the most intense aerial combat of the Pacific War and the ultimate test of radar-directed air defense. Japanese forces launched over 1,900 kamikaze sorties against the Allied fleet supporting the invasion. American ships equipped with SCR-584 radar and massed anti-aircraft batteries created defensive zones of such intensity that Japanese pilots called them walls of steel. The radar systems tracked incoming aircraft from maximum range, providing early warning that allowed combat air patrols to intercept many attackers before they reached the fleet. Those that penetrated the fighter screen encountered radar-directed anti-aircraft fire that began engaging at ranges exceeding 10,000 yards. The SCR-584's ability to track multiple targets sequentially, with operators switching between threats as tactical priorities changed, proved essential for managing the chaotic defensive environment when dozens of kamikazes attacked simultaneously. Detailed analysis of combat actions during Okinawa revealed the system's extraordinary impact. Ships equipped with SCR-584 radar-directed fire control achieved kamikaze kill rates approximately 3 to 4 times higher than ships relying on conventional optical directors. This translated directly into survival. Ships with the new radar systems were significantly less likely to be hit and suffered fewer casualties when they were hit because many damaged kamikazes were destroyed before reaching their targets. The statistical evidence was overwhelming. During Okinawa, American forces destroyed approximately 1,500 Japanese aircraft through a combination of combat air patrols and anti-aircraft fire. Of the approximately 400 kamikazes that successfully struck Allied ships, the vast majority hit vessels that lacked SCR-584 protection. Ships equipped with the radar and properly trained crews achieved survival rates that convinced naval commanders the system represented the difference between mission success and catastrophic losses. Japanese naval intelligence, analyzing the dramatically improved effectiveness of American air defenses, struggled to understand what had changed. Captured documents from Japanese naval headquarters revealed assessments that came remarkably close to the truth while missing critical technical details. A report dated May 5, 1945, noted that American anti-aircraft fire had achieved accuracy impossible with visual aiming alone, and speculated that new electrical calculation methods must be directing the guns. The report recommended that Japanese aircraft approach targets at extremely low altitude, where radar detection might be more difficult, advice that proved partially correct but ultimately insufficient. The SCR-584 could track low-altitude targets, though with reduced range due to radar horizon limitations and ground clutter effects. Japanese pilots attempting low-altitude approaches still faced radar-directed fire, though ships had less engagement time before attackers reached suicide range. Beyond its direct anti-aircraft applications, the SCR-584 revealed capabilities that expanded its operational utility far beyond original design intentions. The radar's extraordinary precision enabled applications that engineers had not initially envisioned. One of the most significant was counter-battery fire direction. Artillery officers discovered that the radar could track enemy shells in flight, determine their trajectory, and calculate the firing position of enemy guns with remarkable accuracy. This counter-battery capability transformed artillery warfare. Previously, locating enemy gun positions required visual observation, sound ranging using acoustic sensors, or flash spotting using optical instruments. All these methods had significant limitations. Visual observation required clear sight lines, often unavailable in combat. Sound ranging was disrupted by battlefield noise and required complex calculations. Flash spotting worked only when observers could see muzzle flashes, impossible in daylight or when enemy guns were concealed. The SCR-584 eliminated these limitations. The radar could detect artillery shells the moment they rose above the terrain, masking the enemy guns. By tracking the shell's trajectory for just a few seconds, the radar's operators could calculate the ballistic arc and determine precisely where the shell had been fired from. This information could be transmitted immediately to friendly artillery, enabling counter-battery fire that could begin landing on enemy gun positions within minutes of their first shot. German artillery units in Italy and later in France discovered that firing on American positions often provoked devastating return fire with impossible speed and accuracy. American artillery, guided by SCR-584 radar tracking, would begin shelling German gun positions before the German crews could displace to alternate firing positions. This forced German artillery to fire fewer rounds from each position and relocate constantly, significantly reducing their effectiveness and exhausting crews with constant movement. The psychological impact on German artillery crews mirrored what Luftwaffe pilots had experienced. These soldiers, who had endured years of combat and understood battlefield dangers, found themselves facing an enemy who seemed to possess supernatural detection abilities. They could not fire without immediately revealing their positions to an enemy whose counter-battery response was faster and more accurate than anything they had encountered on the Eastern Front or in earlier Western campaigns. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Interrogation reports from captured German artillery officers revealed the profound demoralization this caused. Oberst Karl Hoffmann, commanding an artillery regiment in Normandy, was captured in August 1944 after his positions were systematically destroyed by American counter-battery fire. His interrogation, conducted at a facility in England, provided detailed insight into German understanding of Allied capabilities. We understood the Americans possessed good artillery and superior ammunition supplies, Hoffman told his interrogators. We did not understand how they could locate our positions so quickly after we opened fire. We followed all proper procedures. Guns were positioned in defilade, with overhead cover to prevent aerial observation. We limited firing to brief bombardments, then displaced immediately. Yet American counter-battery fire would arrive at our positions within 5 to 8 minutes, with accuracy that suggested they knew exact coordinates. Hoffman continued with growing frustration evident in the transcript. We suspected radio direction finding, though we maintained radio silence during fire missions. We suspected aerial observation, though we fired during poor weather when aircraft could not operate effectively. We suspected French partisans were observing and reporting our positions, though several times we fired from areas that had been secured only hours earlier. Nothing explained how the Americans achieved such rapid, accurate counter-battery fire. It was as if they could see our shells in flight and trace them back to us. His assessment was exactly correct, though he would not learn the technical details of SCR-584 radar until after the war, when declassified information became available to military historians. The radar was indeed tracking German shells in flight and calculating firing positions with precision that seemed impossible by any conventional method. Another unexpected application emerged during the preparations for D-Day. Engineers discovered that the SCR-584's precision tracking could guide bomber formations to targets with accuracy rivaling the best bombardier navigator teams. By positioning the radar system where it could observe both the bomber formation and the target area, operators could provide real-time course corrections to the lead aircraft, guiding the formation to the precise release point for optimal bombing accuracy. This technique, called radar-controlled bombing, proved particularly valuable for attacking targets obscured by clouds or smoke, where visual bombing was impossible. The system demonstrated its value during the pre-invasion bombardment of Normandy's coastal defences. SCR-584 radars positioned on ships offshore tracked bomber formations approaching through heavy clouds that made visual bombing impossible. Radar operators guided the formations to release points above German fortifications, achieving bombing accuracy that stunned both Allied commanders and German defenders, who had assumed cloud cover would protect them from air attack. General der Artillerie Erich Marx, commanding the 84th Corps defending a section of the Normandy coast, survived the initial bombardment, but was killed by Allied aircraft on June 12, 1944. His observations during the first days of the invasion, recorded in messages to higher headquarters, reflected German confusion about Allied bombing accuracy in adverse weather. Enemy bombers are achieving accurate hits on defensive positions, despite cloud cover that makes visual bombing impossible, Marx reported on June 7. This suggests either the use of Pathfinder aircraft with specialized navigation equipment, or some method of guiding bombers' targets without visual reference. Whatever method they employ, it has rendered our defensive preparations vulnerable to attack in weather conditions we believed provided protection. The European campaign's final months saw SCR-584 deployment reach its peak density. By late 1944, the system protected virtually every major Allied concentration in Western Europe. Ports, supply depots, headquarters complexes, bridgeheads across rivers, and troop assembly areas all operated under the protective umbrella of radar-directed anti-aircraft fire. The Luftwaffe, by this point critically short of fuel, aircraft, and experienced pilots, had largely conceded air superiority to the Allies. The few remaining German aircraft that attempted attacks against Allied positions faced defences so lethal that survival rates plummeted to single digits. German pilots flying against defended targets in late 1944 and early 1945 understood they were embarking on essentially one-way missions. The combination of Allied fighter superiority and radar-directed anti-aircraft fire made survival highly improbable. The Battle of the Bulge in December 1944 provided one final demonstration of the SCR-584's capabilities under the most challenging conditions. German forces achieved complete tactical surprise when they launched their offensive through the Ardennes, initially pushing back American units and creating a dangerous salient in Allied lines. Poor weather during the offensive's first week grounded Allied aircraft, neutralizing one of the Allies' greatest advantages. However, SCR-584 radars deployed with American anti-aircraft battalions continued operating throughout the German advance. These units provided critical early warning of German aircraft attempting to support the ground offensive, allowing the limited American forces to concentrate at threatened points. More importantly, the radars continued their counter-battery role, tracking German artillery shells and enabling American artillery to engage German guns, even when visual observation was impossible due to fog, snow, and heavy cloud cover. When the weather finally cleared on December 23, 1944, Allied air power descended on the German salient with devastating effect. But it was the SCR-584 radars that had maintained defensive coverage during the critical first week, when German forces might have achieved breakthrough. The system's ability to function in conditions that blinded optical fire control provided Americans with capabilities German commanders had not anticipated and could not counter. The final accounting of the SCR-584's impact requires examining both quantitative and qualitative measures. Approximately 1,400 complete systems were produced during the war, with production continuing through 1945 as demand remained high despite Germany's imminent collapse. Each system cost approximately $100,000 and required a trained crew of 8 to 12 operators and maintenance technicians. The quantitative impact on anti-aircraft effectiveness was dramatic and well documented. Hit rates improved from approximately 0.2% with optical fire control to 2 to 5% with radar direction, representing improvement of 10 to 25-fold. This meant the same guns and ammunition achieved 10 to 25 times as many kills simply through better targeting. Ammunition expenditure per kill dropped from approximately 1,600 rounds to fewer than 100 rounds, improving logistics and reducing the supply burden on already strained transportation networks. But the qualitative impacts were perhaps even more significant than these impressive statistics. The SCR-584 fundamentally altered the psychological balance of air warfare. Enemy pilots who had previously approached targets with confidence based on their aircraft's capabilities and their own skill now approached Allied positions with dread, knowing that radar-directed fire could track them in any weather and engage with accuracy their evasive maneuvers could not defeat. This psychological impact forced changes in enemy tactics that reduced operational effectiveness even beyond the actual aircraft losses. Pilots who rushed their attacks to minimize exposure achieved lower bombing accuracy. Formations that dispersed to avoid concentrated defensive fire lost mutual support. Aircraft that avoided defended areas left critical targets untouched. The mere presence of SCR-584 systems, even when those systems were not actively engaging, influenced enemy behavior in ways that benefited Allied operations. The German perspective on American radar capabilities evolved slowly, from confusion to understanding to resigned acceptance of technological inferiority. Early reports from pilots and ground observers described impossible accuracy and detection capabilities, without understanding the underlying technology. Middle-period assessments correctly identified radar as the key factor, but underestimated the precision and capabilities of American systems. Final assessments, based on examination of captured equipment and interrogation of prisoners who had operated the systems, revealed the full extent of Allied technological advantage. General der Flakartillerie Wolfgang Pickert, who commanded German anti-aircraft forces defending portions of the Western Front, was captured in May 1945. His post-war interrogations provided valuable insight into German understanding of Allied radar capabilities. Pickert had access to intelligence assessments and technical evaluations of captured Allied equipment, making him one of the most knowledgeable German officers regarding Allied air defense technology. We understood by early 1944 that the Americans possessed radar systems with extraordinary precision, Pickert told his interrogators. Captured equipment confirmed this. What we could not match was the integration. American systems combined radar detection, automatic tracking, continuous position calculation, and direct gun-laying commands in a single coordinated system. Our equipment could perform individual functions, but integration lagged significantly. The microwave radar operating at 10 cm wavelength provided resolution our longer wavelength systems could not achieve. The automatic tracking eliminated human lag in following maneuvering targets. The electronic computers calculated firing solutions faster than our mechanical systems. Each individual advantage might have been small, but combined, they created a system significantly superior to anything we fielded. When asked whether better German radar would have changed the war's outcome, Pickett's response reflected the broader German understanding of their strategic situation by 1945. But the fundamental problem was not any single technology. American industrial capacity produced overwhelming quantities of everything: tanks, aircraft, ammunition, radar systems, all in numbers we could never match. Better radar would have made our defenses more effective, but would not have changed the strategic balance when the enemy possessed 10 times our resources. The Japanese perspective, gathered from post-war interrogations and examination of captured documents, revealed similar patterns of initial confusion, gradual understanding, and ultimate resignation to technological inferiority. Japanese radar development had lagged significantly behind Western powers throughout the war. Japanese early warning radars provided basic detection capability, but precision fire control radars comparable to the SCR-584 never entered Japanese service in significant numbers. Vice Admiral Takejiro Onishi, one of the principal architects of kamikaze tactics, understood better than most Japanese commanders how radar-directed American defenses had undermined conventional attack methods. His decision to adopt suicide tactics was influenced partly by recognition that traditional bombing and torpedo attacks had become prohibitively costly against American ships protected by radar-directed fire. Onishi's reasoning, documented in planning papers recovered after the war, was brutally pragmatic. If conventional attacks achieved only 5% hit rates due to American defenses, then 95% of attacking aircraft were lost without accomplishing anything. If those same aircraft deliberately crashed into targets, hit rates might reach 25 to 30%, with all aircraft lost but many achieving their mission. The suicide tactics were not primarily motivated by fanaticism, but by cold calculation that radar-directed American defenses had made conventional attacks strategically futile. The post-war examination of SCR-584 systems by Soviet technical teams revealed how completely the radar had achieved its design objectives. Soviet engineers, whose nation had received some American radar systems through Lend-Lease but not the SCR-584, were particularly interested in the automatic tracking systems and fire control integration. Soviet radar development had followed different paths, emphasizing simpler systems that could be produced in larger quantities rather than sophisticated systems requiring complex manufacturing. The Soviet assessment concluded that the SCR-584 represented a technological approach that emphasized quality over quantity, precision over simplicity, and integration over individual component performance. This reflected fundamental differences in American and Soviet industrial philosophies that would influence Cold War military development for decades. The legacy of the SCR-584 extended far beyond its immediate wartime applications. The system established principles of radar fire control that influenced all subsequent development. Modern air defense systems, from ship-mounted missile systems to ground-based anti-aircraft complexes, descend directly from the SCR-584's integration of precision tracking radar with automated fire control. The technical lineage is clear and well documented. Post-war American radar development built directly on lessons learned from SCR-584 deployment. The Nike Air Defense System, deployed beginning in the 1950s to protect American cities from Soviet bomber attack, used tracking radars that were evolutionary descendants of the SCR-584. The Aegis Combat System, currently protecting American and Allied warships, traces its technical ancestry directly to World War II radar fire control systems. The principle of automatic tracking, where radar systems lock onto targets and follow them without continuous human input, became fundamental to all subsequent military radar applications. The SCR-584 pioneered this approach in operational systems, demonstrating that electronics could track targets more precisely and consistently than human operators. Every modern radar system uses automatic tracking derived from principles first proven in combat by the SCR-584. The human story of the SCR-584 deserves recognition alongside the technical achievements. Thousands of soldiers and sailors operated these systems under combat conditions, maintaining complex electronics in field environments that were hostile to sensitive equipment. These crews worked in all weather, under air attack, often while exhausted from sustained operations. Their technical competence and dedication made the radar's potential effectiveness a battlefield, a reality. The maintenance burden was particularly challenging. Each system contained approximately 3,000 vacuum tubes that generated enormous heat and failed regularly. Crews needed to diagnose failures, identify defective tubes among thousands of identical-looking components, and replace them while the system remained operational. This required training programs that produced graduates with skills comparable to civilian electronics engineers, a significant investment in education that paid dividends throughout soldiers' post-war careers. Many veterans who operated SCR-584 systems during the war entered electronics and engineering professions afterward, using their military training as foundations for civilian careers. The system's complexity required such sophisticated understanding of electronics principles that operators received what amounted to college-level technical education, compressed into intense military training programs. This represented one of the war's many inadvertent contributions to post-war technological development, as thousands of technically trained veterans entered the civilian workforce. The story of the SCR-584 also illustrates the importance of industrial capacity and systems integration in modern warfare. The radar itself, while technically sophisticated, was not revolutionary in the sense of being based on entirely new scientific principles. British scientists had invented the cavity magnetron that powered the system. The mathematical principles of ballistics and tracking were well understood. The electronic circuits used conventional vacuum tube technology. What made the SCR-584 revolutionary was the integration of these components into a complete system that actually worked under combat conditions, and the industrial capacity to manufacture such complex systems in quantities sufficient to affect strategic outcomes. American industry produced 1,400 complete systems during the war, each requiring approximately 30,000 person-hours of skilled labor. This production achievement rivaled the technical design achievement. Germany possessed competent engineers and scientists who understood radar principles and could design sophisticated systems. But German industry, operating under constant air attack, critically short of critical materials, and forced to prioritize production of basic weapons like tanks and aircraft, could not manufacture precision radar systems in strategically significant quantities. Technical knowledge, without industrial capacity to implement that knowledge, proved strategically worthless. The SCR-584's counter-battery application, while less celebrated than its anti-aircraft role, may have saved more Allied lives overall. Artillery caused the majority of casualties in World War II, far exceeding losses from small arms fire or armor. Any technology that reduced enemy artillery effectiveness directly reduced friendly casualties. By enabling rapid, accurate counter-battery fire, the SCR-584 suppressed German artillery far more effectively than previous methods. German artillery units that might have fired dozens of rounds from a position before displacing were now forced to fire a few rounds and immediately relocate or face devastating counter-battery fire. This reduced German artillery's effectiveness significantly, providing Allied infantry and armour with reduced exposure to what had been the war's deadliest weapon. The lives saved by this application alone might number in the tens of thousands, though precise figures are impossible to determine. The final assessment must acknowledge both what the SCR-584 achieved and what it represented. As a weapon system, it transformed air defence from an inefficient expenditure of ammunition into a genuinely effective countermeasure that imposed real costs on enemy air operations. As a technological achievement, it demonstrated that precision electronics and sophisticated systems integration could create capabilities unattainable through mechanical systems alone. As a strategic factor, it contributed meaningfully to Allied victory by protecting critical assets and denying enemies freedom of action in airspace above Allied-controlled territory. But most fundamentally, the SCR-584 represented the Allied advantage in industrial capacity, technical education, systems engineering, and resource availability. These advantages, multiplied across thousands of weapons systems and millions of tons of equipment, proved decisive in determining the war's outcome. March 15, 1944, Oberstleutnant Friedrich Weber stood amid the ruins of his coastal battery near Anzio, surveying damage from the bombing raid his guns had failed to prevent. The American bomber had remained invisible throughout its approach. His radar screens had shown chaos rather than clear targeting information, and the bombs had fallen with precision that suggested the enemy could see in complete darkness. Weber would survive the war, later learning about the SCR-584 radar system that had rendered his defences obsolete. In post-war interviews, he reflected on that night in March 1944, when he first understood that Germany faced enemies whose technological capabilities exceeded German comprehension. "We believed we understood the limits of what was possible," Weber recalled. "We built our strategies around those limits. When the Americans demonstrated they had exceeded those limits, not through marginal improvements but through revolutionary advances, we should have understood the war was already lost. But we fought on because soldiers follow orders, even when the strategic situation is hopeless." The examination of one radar system revealed more than technological specifications. It revealed the decisive advantage that integrated systems, backed by overwhelming industrial capacity and virtually unlimited resources, provided to nations that possessed them. German and Japanese commanders, who encountered SCR-584 directed defences, learned the same lesson that U-boat commanders had learned about centimetric radar. Superior individual skill and tactical excellence cannot overcome systematic technological disadvantage when that disadvantage is deployed at strategic scale. The SCR-584 tracked targets with precision measured in yards at ranges exceeding 15 miles. It provided fire control data accurate enough to place anti-aircraft shells within lethal distance of targets that previous systems could barely detect. It worked in any weather, day or night, through conditions that blinded optical systems. And, most devastatingly for enemies who encountered it, the system was manufactured in quantities sufficient to protect virtually every significant Allied position. Japanese pilots approaching ships protected by this radar understood they faced nearly certain death if they remained in the defensive zone long enough to attack. German pilots learned the same lesson over European battlefields. German artillery crews discovered that firing revealed their positions to counter battery fire of impossible accuracy and speed. These men, skilled professionals fighting for causes they believed in, found themselves defeated not by superior courage or better tactics, but by electromagnetic radiation manipulated through electronics they could neither see nor comprehend. The strategic consequences extended beyond immediate tactical results. Air forces that cannot operate over enemy territory lose their ability to influence ground battles. Artillery that cannot fire without immediate counter-battery suppression loses its effectiveness. Defenders who cannot hide their positions must either accept casualties or cease defensive fire entirely. Each degradation in capability cascaded through operational and strategic levels, ultimately contributing to defeat. When Allied scientists and engineers celebrated the SCR-584's success after the war, they recognized they had created more than an effective weapon system. They had demonstrated that modern warfare increasingly depended on technologies that integrated multiple disciplines: physics, electronics, mechanical engineering, and systems design into weapons whose effectiveness derived from sophisticated coordination rather than simple destructive power. This principle would dominate military development throughout the Cold War and into the 21st century. The radar installations that protected Allied positions during World War II, tracking targets with primitive electronics and vacuum tube computers, established the foundation for modern air defense systems that track hundreds of targets simultaneously using solid-state electronics and digital computers. The evolution is direct and unbroken. Every principle pioneered by the SCR-584, automatic tracking, precision fire control, all-weather operation, remains fundamental to contemporary systems. The human cost and strategic implications of this technological revolution deserve final reflection. Thousands of German and Japanese aviators died in attacks against Allied positions protected by radar defenses they could not defeat. These men were not cowards or incompetents. They were skilled professionals who found themselves fighting enemies equipped with technologies that rendered their training and courage strategically insufficient. Their sacrifice changed nothing in the war's outcome because the technological gap was simply too large to overcome through human determination alone. The lesson, documented in thousands of combat reports, interrogation transcripts, and post-war assessments, was clear and unforgiving. Modern warfare rewards nations that combine scientific knowledge, engineering expertise, industrial capacity, and resource availability into integrated systems deployed at strategic scale. Individual technical advantages matter less than systematic superiority across multiple domains. The SCR-584 represented this systematic superiority made tangible, a radar system that saw through darkness and tracked targets with precision that seemed magical to enemies who encountered it. When Oberstleutnant Weber examined the wreckage of his radar installations near Anzio, trying to understand what had overwhelmed his defenses, he was conducting an autopsy on German technological confidence. The Americans had deployed capabilities that German engineering could not match, and German industry could not produce in competitive quantities. That realization, multiplied across every technical domain, from radar to aircraft engines to logistics systems, explained Germany's defeat more completely than any analysis of military strategy or battlefield tactics. The examination of what one radar system achieved reveals the electromagnetic dimension of warfare, where victory was determined by physics and engineering as much as by courage and skill. The Japanese pilots, who never expected radar to track 40 targets simultaneously in total darkness, learned the truth too late to affect their strategic situation. By the time they understood Allied capabilities, the technological gap had become unbridgeable, and defeat was mathematically certain. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.